Hello everyone. So today we are going to solve a simple problem on nuclear physics. Particularly, we are going to focus on certain concepts like the radius of the nucleus, how we can solve some problems related to the radius of the nucleus. Um, so we have a problem that related to this concept, and the problem goes something like this. Suppose we have two nucleuses and they are touching each other at some point. This is nucleus 1 and this is nucleus 2. It has atomic number A1, it has atomic mass number A1 and at mass number A2, and it has some atomic number Z1 and atomic number Z2. So the question is that what is the potential energy due to electric repulsion between these two nucleus? So it is actually a pretty simple problem, just formula based. There is no deep concepts here right now. So the question is that you have two nucleuses and they have this different atomic numbers and different mass number, and these nucleuses are touching each other, but because nucleuses are positively charged, so there will be a repulsion because they have protons and neutrons, and these protons will repel each other from so now we need to calculate the potential energy due to the repulsion between these two charges. So there is first we need to calculate the distance between these two centers. We can think that all this charge distribution, assuming that we consider only spherically symmetric distribution of charge in the nucleus, and this is also spherically symmetric distribution of charge. All the protons are spherically symmetrically, I mean, you can think that assume that this you can assume that all the charge in this nucleus is distributed in such a way that there is no anisotropy in the distribution of the charge. So this is an assumption which people assume in such a problem, and then you can just think that all this charge is concentrated here, all the positive charge is concentrated in the center. So we need to first calculate the distance between these two things. So there is an empirical relation between the radius of a nucleus and the mass number of the nucleus, and this empirical relation goes something like r is equal to r naught a to the power 1 by 3, where r naught is somewhere around 1.1 femtometer. So this is just some experimental value. Now the question is we need to calculate the distance between these two. Okay, so the radius r1 of this this is r1 and this is r2. Okay, you can just think that this is the distance which is r2. So r1 is r naught a1 to the power 1 by 3, and similarly r2 will be r naught times a2 to the power 1 by 3. So now it's simple, we just need to add it, and uh, mm, we will need to just add this. So the effective distance between this between the charge distribution of this nucleus and the charge distribution of this nucleus can be taken as the distance between these two. So basically this is just center of charge. Okay, like center of mass you have center of charge. We will get to different problems where the charge distribution is not spherically symmetric, in that case we will calculate the center of charge, and from there we will do all these calculations again. But for the moment, because it is a very simple problem, we just uh, stress that this is a spherically symmetric charge distribution in the nucleus, and so the effective distance between the two charges will be r1 plus r uh, r2. Okay, so we know the uh, distance between these two centers of charge. So our problem has now reduced to very simple situation where we have some charge here, some charge here. They are separated by a distance r equal to r1 plus r2. And what is the charge of this? So it is very simple. For this it will be, say, q1 is equal to z1 times charge of a proton. Okay, similarly here it will be z2 times charge of a proton. So these are positive charge. So now we need to simply just calculate the potential energy between these two. Potential energy will simply be 1 by 4 pi epsilon naught, and we just take q1 q2 by r. So this actually just converts to 1 by 4 pi epsilon naught q1 q2 by uh, so we just take these values and substitute it. So we have this r naught here as a common value, and a1 to the power 1 by 3 plus a2 to the power 1 by 3. So this is our answer. So effectively our answer is that the potential energy has the value 4 pi epsilon naught. q1 is just z1 z2 qp. Qp is charge of proton by r naught a1 to the power 1 by 3 plus a2 to the power 1 by 3. So yeah, sorry, there should be a square here because q1 is z1 qp and q2 is also z2 qp. There will be a square. So this is our answer. Thank you.